where people sitting on the floor. I'm always super impressed by that. Maybe raise your hand if you have a free seat next to you. Okay, 1, 2, 3, 4. Maybe some of the people sitting on the floor want an extra seat. So, we're going to talk about Mars. Why? Well, because it's a planet, because it's round, and because it's red. So it's nice. That's our job. We are Martians. Sheila is a planetary scientist, so she uses the data and she finds out stuff, and she's going to tell you about it. I'm Armel. This is my colleague Andy.
Hello.
He flies Mars Express, or MexGyver, as we like to call it, because this mission is just unbelievable. I fly the TGO orbiter, and basically once Sheila has told you all about the science, we're going to explain to you why we sweat so much blood trying to get her the science. Yeah, I think that's it. One last small thing. We are very passionate about what we do. We have thousands of stories to tell. We're going to try to keep to the time. When we get excited about things, we start to speak very, very, very fast. So if you get too fast and you don't understand anything, just raise your hand and we'll know. Okay, let's go.
Okay, everyone. Good afternoon. I'm so happy to be here and share my story with you because I'm also a big Star Trek and Stargate fan, so I'm very happy. So I will bring you to Mars today. But where is Mars? So Mars is the 4th planet from the Sun. It's actually one planet further from Earth. And you can see Mars with your naked eye if you look at the sky at specific time of the year. But also, if you have a telescope, you can see some of the details on Mars. So you see it's a reddish planet, but you also see some dark lineated features and also the polar cap, which is very bright. So this is not a surprise that Giovanni Schiaparelli thought that what he's looking at, those dark lineated features, are actually channels made by aliens, and there is a civilization on Mars. So he made a map in 1890, and this is his observation. But of course, we know that much better today. This is an image of the Hubble Space Telescope. Hubble is orbiting around Earth and takes also pictures not only from the universe but also from the planets of our solar system. So we see that there are no channels like artificial channels on Mars, so there is no civilization there. And of course, so we are sending spacecrafts since 50 years to Mars, so we have a bunch of data to work with, and my specialty is remote sensing, so I'm using the data from various orbiters in order to reveal the secrets of Mars. But comparing the atmospheres of Mars and Earth, so what we can say is that Earth has mostly an oxygen and nitrogen atmosphere, and Mars has mostly CO2 and very, very little oxygen. And also, the other big difference is that the pressure, the atmospheric pressure on the surface of Mars is so teeny tiny that we have the same pressure about 20 kilometers from the surface on Earth, so much above the commercial aircrafts where they fly. So those are flying about 10 kilometers, so at 20 kilometers, so the air is really thin. Comparing the size of the planets, so Mars is a little bit larger than half of the size of Earth, and also the gravity is lower there. So if you weigh like 50 kilo of then you weigh around 90 kilo on Mars. It's a good deal, I think. So, and here you can see a map from Mars Global Surveyor. This is the topographic map from Mars. You can see So what you can see is that there are highly elevated areas marked with the red and yellow colors, and low elevated areas are with the blue in the north. So we call it highly cratered highlands and low-lying northern lowland areas. And what you can see more, there are two volcanic regions. One of the regions is above my head, at the dichotomy of the lowlands and highlands. It's called the Elysium. And the other volcanic area is called the Tarsis, which is above my head. So there are three large volcanoes, and the fourth one, which is called Olympus Mons, and this is the largest volcanic volcano in the solar system. Oh. And one of the most interesting things are also channels, but not artificial channels, but natural ones. So those are located in this area. So channels are flowing from the highland area to the northern lowlands, and I will show you some nice pictures of those. So, but how Mars looks like today? It's an extremely cold and dry environment with very thin atmosphere, and dust covers everything, also including the rovers which are studying also currently the surface. And also there is high radiation. So we have to solve this issue before actually we go to Mars. But Mars was different around 4 billion of years ago, so we call this era as Noachian. So we think that the atmosphere was thicker, and also liquid water was present on the surface. So there were rivers, there were lakes, and also maybe an ocean in the northern lowland area. Okay, so there are plenty of evidences of water. First, I would like to talk about the outflow channels. And this is an example of Casey Valleys. So, Casey Valleys is about 1,600 kilometers long, tens of kilometers wide, and in some locations it is 2 to 3 kilometers deep, so it's deeper than Grand Canyon. And just to compare the size to our terrestrial rivers, so Casey Valleys is the example up there on this in this image subset, and there is Amazon and Mississippi at the bottom. So you see that Amazon and Mississippi are teeny tiny rivers compared to these outflow channels on Mars. And here is the topographic image of one segment of Casey Valleys, where it enters the northern lowlands area, enters the Crissy Planitia, which I will be talking about later. Also, other evidences are rivers which we also have on Earth, of course. And I need to mention that this image was made by Mars Express, the European Agency's Mars Express orbiter. And also the camera was developed by the German Aerospace Center, DLR, in Berlin. So, thank you so much. It is taking images in the past 20 years, so it does great science, so we hope we will get more years of operation. So, thank you. And also, here is the topographic image, so highly elevated areas with red and blue with the low elevated areas, and you see that the rivers are meandering from top to the bottom. Also we have lakes, craters which were filled up by water at some point of time, but we know that these lakes were having water for a long period of time. So in this example, you see the Jezero crater. This is the landing site of NASA's Perseverance rover. And just to show you this feature on the left, so it's the Jezero Delta. So rivers, when they are transporting sediments and they enter to a lake or a sea, they put down all those sediments they transport over time, and then they create this lobated foam. And also, we can see a nice example from Earth. This is the Danube Delta. So Danube is actually originating from Germany, and it enters the Black Sea in Romania. So I think there is a nice similarity. Also on Mars we have polar ice caps. The composition of these ice caps is CO2 and water ice. And we also have glacier-like features in the mid-latitude areas. On the left you see a nice example that ice flown from the top of the image down to one crater and ended up in a larger one. We call this area as an hourglass crater. But these features are actually much younger than those river valleys I showed you before. There are also other evidences of water. So these are minerals, and especially clay minerals we are looking for, because these minerals formed around 4 billion of years ago, when Mars was probably wet and warm, so had a thick atmosphere and had water on the surface. And this type of mineral is good to preserve biosignatures. Earth, according to the Federation Planetary Scheme, Earth is a Class N planet. But where is Mars located here? Mars is a Class K planet, so as we know it today. But maybe in the past, Mars was a Class L planet, which means that it was probably habitable for a short period of time. And now I would like to talk about one of my favorite projects, which is the ExoMars program. And it's the best project of ESA's, yes. I don't want to be biased. So it comprises 2 missions. The first mission was launched in 2016, and it is the Trace Gas Orbiter, and it also had the Schiaparelli demonstration lander, so you can see it on the top. And what I'm working with is the Rosalind Franklin rover, which you can see in the middle of this picture. So we have very interesting science objectives to fulfill during the mission. So the Trace Gas Orbiter is actually studying the atmosphere, and trace gases in the atmosphere of Mars, and it does it very well, and also provides relays data from surface assets from NASA back to Earth. So it's not only doing science, but does a service as well. And the rover mission, so just a little bit about Rosalind Franklin. So Rosalind Franklin was a chemist and crystallographer who helped to unreveal the structure of the double helix of DNA, so the basics of life. And that's why the rover was named actually after her. The first science objective is to search for past and present life on Mars. The other objective is to drill down 2 meters and study the material from that depth, because we think that radiation is not going through that deep to the subsurface, and we might find pristine material there. So we have higher chances to find something if we drill down. And the third objective is, of course, to study the geologic processes and the environment of the landing site. So how big the rover is? So it is about 300 kilograms 300 kilograms. And also we can measure the size in meters, but also in triple sizes. So we have the rover. It's about 2.5 meters wide with the deployed solar arrays, and about 2 meters tall. So it's 10.6 triples. So maybe it's a fun fact. Yeah. With the fur. It's not like a wet cat. And if we want to compare the size, then there is Delta Flyer here and some officers working on it, and Rosalind Franklin is just right next to it. Okay, but where we want to go, so where we want to go to Mars to search for life, so there are science and engineering constraints to find a suitable landing site. So in Star Trek, you see that most of the times Voyager says, oh, a couple of light years away we have a planet and we have some minerals we need, and this is 200 meters in the subsurface, and they just say it in 5 seconds basically. They find it in 5 seconds. So it doesn't work like that, unfortunately. So we have science constraints here. So we want to find a terrain which is very old, and means that those rocks were formed like 4 billion of years ago. And also we could find this type of clay minerals I mentioned, and also some traces of water activity. And on this map you see with the blue lines, there are actually rivers, and with the yellow dots you see the occurrence of these clay deposits. But the issue is that we cannot go anywhere we like. So we have lots of constraints. We cannot go higher than 25 north. So all the areas we cannot go, marked with the blue. Maybe you cannot see that, but so there are areas only between the 25 north and 5 south where we can go, and this is because we use solar panels, and the equatorial region gets most of the energy. So we need that to operate the instruments. And the second issue is the elevation. So because we decelerate the lander with parachutes, we need a thick enough atmosphere. So we have to go deep down, lower and lower, in order to decelerate for enough to soft land on the surface. And also for the operation, we would like to have a very flat, smooth surface. So after 5 or 8 years of landing site selection and lots of meetings, we finally found the landing area, which is called ESA-Panel. So you can see it up here. This is located at the edge of Planitia, where all these outflow channels entering the northern lowlands, and in northwest part of Arabia Terra, which was also the landing site for Opportunity rover, somewhere in a different part of Arabia Terra. But you can see that there are rivers nearby, and also there are indications for clays. This is a zoomed-in image. You see, this image was also made by the HRSC camera. Thank you, Germany, again. So what we can say is that the landing site might have a geology which was characterized by fluvial activity, and also if Planitia harbored an ocean at some point, then this ocean must have been connected with the landing area, and it will be very cool to figure this out if we get there. And my part in the project so far was to coordinate a geologic mapping campaign, and I worked with my colleague Peter Fordon from Open University, and we created a very high-resolution geologic map, also with the help of the entire science team. And what you can see is that there are different colors, so the map is very colorful, which means that the geology is very colorful, very, very diverse in this terrain, so it's very interesting to look at. And anywhere we go, which is blue and orange, then that means that we can find these clay minerals, and we have good chance to study the best material available to search for signs of life. And here you see just a part of the landing site. So it's a 3D image from Cassis camera. Cassis is on board the Trace Gas Orbiter, and that was developed by Switzerland. So thank you, Switzerland, for giving us very nice data. And here, this is a false color image, so this is not the real color of Mars. But anywhere where you see orange and blue, so there are clays we are looking for. And this is actually my last slide, and it's a nice image of Cassis, and I hit the rover somewhere in the middle, so maybe you can see it. And we are hoping that we can launch the mission in 2028 and get to Mars and answer these very important questions. So, and now I think I'm giving the mic to Andy, and he will be talking about his MacGyver experience. Thank you.
So, once upon a time... No, okay, so...
Library of Mission to Mars.
Well, first, why do we call your mission MacGyver?
Oh,
I think it's important to explain that.
just because we have so many improvised things and fixing problems. So another thing that Armel didn't tell you, we do talk quickly when we're excited. I'm also Scottish, so you've got to put up with that as well.
Yeah, get ready to raise your hand.
Yeah. So we just started with the mission. Yeah. Okay. So about Mars Express. Why it was called Mars Express is partly because it was so quickly developed. A thing about the orbits of Mars and Earth is they're not circular, they're elliptical. And also, about every 17 months, Mars and Earth will pass close to each other. And in 2003, it was predicted that the point where Earth and Mars were closest to each other was also the point where the two orbits were closest to each other. And what this meant was we were able to, well, the distance is shorter, which means less energy per kilogram to launch something to Mars. So we could therefore launch a small but still effective spacecraft on quite a small launcher and do this relatively cheaply. And so that's what we did.
So how often does it happen actually that they are so close together?
Thank you for reminding me that. This only happens every 60,000 years. So it was quite an opportunity. The problem was, in order to do this cheaply as well and quickly, was that we had to basically use as many off-the-shelf components as possible, and so this was a real MacGyver job. So, the first thing was, for the body propulsion, we took a French communication satellite, a Eurostar 2000, and then we slapped on some solar arrays from an American communication satellite, the Global Star. Then for all the electronics, which is like all the computer systems, the radios, various things for controlling the spacecraft, we had Rosetta, which is also a mission. So Rosetta was already developed for deep space, and also because we already had the spacecraft being developed for us, we were already familiar with the system, so it made a lot of sense to use Rosetta for all this part. But then we need a payload. And where this came from was the Russian Mars 96 mission, which failed. There was still a load of flight spares left over, so we basically read that we covered, and took as many instruments as we could from that, which included HRSC. So, and then when we mixed all these together, we came up with Mars Express, which cost us actually 150 million euros, which may sound a lot, but it's very cheap for a space mission. And if you think, how much does a Hollywood film cost me? And how many of them get made each year? Mars Express was designed to last for 2 years on Mars, and next Friday we'll be celebrating its 20th year in space.
Wow.
In other words, we use very, very strong duct tape.
Yes, we do.
But I have to say, so 150 million now wouldn't be enough to create a Mars Express-like satellite. So we need a bit more money to do that.
Or more spare parts. Okay, the next one. Talking Scottish and French at the same time. Why would we want to do that? So, as we said, 20 years ago, ESA decided to launch Mars Express, which, apart from Giotto, was basically the first interplanetary mission from ESA. And everything was nice and fine. Mars Express was happy and alone around Mars, sending lots of data, speaking mostly green. And then Earth would talk to Mars Express to send some commands, and would also speak green to Mars Express. And then a few years later, in 2016, we launched a second spacecraft, TGO. Doing this, we actually doubled the size of the ESA fleet around the Mars, which, you know, is quite a feature. And then, because green language provides a lot of information. So when I say green, it's basically the bandwidth that we use, the frequency that we use. It's called the X-band. And basically it goes very fast. We can send a lot of data, and pictures require a lot of data, so we like to use this bandwidth a lot. The thing is that for the commanding, TGO was also only understanding green. And this caused problems because when we were commanding both spacecraft at the same time, we had, well, basically a third shade of green, and the two spacecraft got completely confused by that and did not really understand to whom we were talking. This, in effect, meant that the capacity for commanding to Mars Express got divided by 2, because we had to talk to 2 spacecraft with the same amount of time, and we could only do 1 at a time. Luckily, next being an old spacecraft, it was also equipped with a transponder, which were using another length, which is, sorry, one small thing, yeah. So, both spacecraft talking to Earth at the same time in different shades of green is not really a problem, because we have many antennas on Earth, and we are here. So we can tweak them, and we can exactly choose what color of green we choose. So this goes perfectly well. NASA uses it all the time. It's called multiple spacecraft per antenna, but it's nothing new. As I was saying, Mars Express can also understand red. What is red? It's the S-band. It's basically mobile phone. So today we're not allowed to use this anymore because, well, people use mobile phone, and if we were to communicate continuously with our spacecraft using this, you would hear us on your phones all the time. You don't want that. So we can do it from a small set of antennas which are in the middle of nowhere, and therefore we don't disturb anyone. One of these antennas is actually in Australia. It's one of our ESA antennas. And the beauty of that is that this antenna can talk to both spacecraft at the same time in red and in green. So we can have duplex communication with both our satellites. We call it MUPA, multiple uplinker antenna. We can do that, us, NASA cannot. But it's only possible because of MEX. MEX is the best.
Yes, yes. Oh, okay, yes. Another story from the...
This one's great. I like it.
This took up a year of my life, this mission, this project, and it's going to be done in 4 slides. Okay. So, in 2013, there's the Siding Spring Observatory in Australia, and it spotted a comet. And they plotted the trajectory, and it worked out that in October of 2014, it would pass very close to Mars. Now, I need to animation. Okay, a comet passing close to Mars itself is not a problem. Comets are tiny, really, really tiny, and space is big, very, very big. I've had to really, really exaggerate the size of the comet here so it even shows up at all in this image. The problem with comets is they are made of ice and dust, and when they come close to the sun, the ice starts to boil off, lifts the dust away from it, and it forms what we call a coma, a large cloud. Now, I had to exaggerate the size of the comet itself, we call a nucleus. In this case, I've actually had to go the other way because it wouldn't fit on the screen, because this cloud becomes enormous. And, okay, the other part of this cloud forming is that we also get solar pressure, which then pushes some of the particles away, and then we get the tail of the comet, which is what we know comets for. But what was going to happen, we predicted in 2014, was that Mars would pass through the coma. And this is potentially bad. So, but luckily, ESA had already got 2 missions which had gone near comets, so we could maybe learn something from those.
But Rosetta had not even arrived yet. Rosetta
right.
arrival was November 2014. So technically, MEX was the second comet observatory and the third.
Fine, I'll put it there. Okay, so but the 2 other missions which were designed to go to comets, let's put it that way then, was Giotto, which was in the 1980s, which went to Halley. I remember sitting in primary school drawing pictures of my books when I should be learning how to spell. And Rosetta, which, well, actually, let's talk about Giotto first, because Giotto took a very interesting technique of going to a comet. It was designed to basically fly fast and charge through the coma and get the first images of the nucleus of a comet. And so it was built tough. The white section you see, I'm trying to get this squishy point here. The big white bit you see on the Mars Express side was multiple layers of aluminium, which we call a Whipple shield. So if anything smashes into that, it would break and then keep breaking as it passes through layers, and that would protect the spacecraft. It's also spin stabilized, which would be a lot more resilient to impacts. And you see this little white thing on top? That's like a periscope with the cameras. So the cameras would have a little mirror to look around the shield to protect them. And it was tough. And it went off and did its job, and it was great. Rosetta, on the other hand, took a different approach. It was going to sneak up on a comet, come very, very close, and then, well, drop a robot on it and harpoon it. So,
as you do.
So, we're built a lot more like Rosetta, so we would prefer it if the comet we're going to encounter would give us the conditions close to Rosetta. So the biggest thing influencing us is going to be the energy of the particles, which is going to be related to the square of the velocity. So with Giotto, the closing speed was 68 kilometers per second. I don't know how many of you last night saw the ISS pass overhead, but that was going about 7 kilometers per second. So this is almost 10 times faster. This is insane speed. Whereas Rosetta was about 1 meter per second, which is walking speed. So then we had to wait for the astronomers to work out what were we going to experience. Was it going to be like Rosetta, like the speed my mum goes up when she goes to get a cup of tea, or was it going to be full Leroy Jenkins? The answer was Leroy Jenkins. So, okay, to be fair, this is only 8 times the speed of the ISS. So, the other aspect you would think of though is, okay, this determines the energy of an impact. When it hits you though, the closer you are to the comet, the more likely you are to be struck by a particle. So, we can forget about Rosetta now because we're not in that category. We're not my mum going for a cup of tea. Giotto passed about 600 kilometers from the comet, which is insanely close. We were going to be 134,000 kilometers. It's like, that's not so bad. Except that Giotto started taking impacts at 500,000 kilometers, and it hit 12,000 times. One impact was so severe it took the onboard systems 32 minutes to recover. The little periscope I showed you got torn off. It took a beating, but it did complete its mission. So, looks as though we weren't in for a good time. So, I made up my plans over a year or so. This is my advice on what you should do if you find yourself being attacked by a comet. 1, make yourself as small as possible. Silhouettes of Mars Express. The body's basically a cube, so smart which way we orientate this, you're going to basically present the same area. The arrays, they stick out like this. This way, sorry, would present an area about 14 square meters, whereas we could put an edge on, it's not very much at all. We were very, very lucky in that the comet was approaching at about 90 degrees to the sun, so we could afford to hold this position for quite a long time and reduce our surface area down to about 3 and a bit square meters. But the next thing you should do is use a shield, because that's what Giotto did. Now, I'm going to apologise for this picture because it looks horrible. Oh, just let your eyes take it in. Right, the coloured components are all basically components inside the spacecraft. Once you absorb that, it doesn't look so bad. The white parts are all panels of the spacecraft. These are aluminium honeycomb, which kind of looks like cardboard, but it's made of aluminium. One face of the spacecraft has very little components on it, which is the side with the high gain antenna. And that is also good because the high gain antenna itself gives us layers. So the idea was we would point that at the comet, and then we'd use that as our quickle shield, so that would hopefully smash through, not do any damage to the spacecraft. The other thing you should do is hide behind something. This is a diagram that was drawn by Flight Dynamics at the time when we were going through the comet. And this basically is like a comet's eye view of heading towards Mars. So the big ellipse you see is the orbit of Mars Express, and where it crosses, where it crosses Mars, that will be passing behind the planet for about 27 minutes. The problem is we expected the passage through the coma to be about 5 hours. So what Flight Dynamics did was they calculated where they expected the peak of the number of impacts to be, and then they rephased our orbit so that we would be behind Mars at that precise minute. They had to do the burn to change the phasing of the orbit. I think it was something like 5 months in advance. And then they got the timing exactly right. So that was really quite advanced maths by them, but that was where this is what my year of work was actually this slide. But there's one other thing you should do if you get attacked by a comet, which is you should be lucky. And we were lucky. This is the image of the comet 1 month before. Now, as the comet got closer and closer, we got more and more observations. And it turned out that the comet appeared to be coming from the Oort cloud. It seemed to originate from about 1 light year out, which is quite a long way away. And as it came in, it turned out to be a smaller comet than we expected. Therefore, the coma was smaller. But also, for some reason, the activity of the comet was reducing. So then, again, it's not producing so much material, we're less likely to strike. And another aspect is because it wasn't producing this material, sometimes a comet can produce a jet, which acts like a rocket, and can start to modify its orbit. That did not happen with us. So we got lucky there. And one other weird thing happened. This is the sun. The sun spewed out 5 days before the comet impact, a massive coronal mass ejection. How do you describe that?
It's a big burp.
It's a big burp. The sun burped, and the coronal mass ejection hit Mars at the same time as the comet, and it blew away most of the particles, we think. And what happened then was basically, after we run our checks, we discovered we discovered no damage at all. So, I guess the moral of the story is when you're facing what seems to be a impossible situation, you do everything you can to nudge the odds in your favour, and you just have to accept what the universe has to solve for you. So. I know.
Okay, what's the next direction? Don't remember. Yeah. Lost in space. Believe it or not, this actually happens to us. So, we have on board spacecraft little cameras, which we call star trackers, which we use to know where we're looking at. How do they work? They use triplets, not triples, triplets. They look at the sky, they take pictures, and then, like a sailor lost at night in the middle of the sea, it recognizes constellations. In this case, it's always by threes. And because the magnitude of the stars, so how much they shine, is different for every star, and because all the shapes of the triangles are different, by matching what they see to the map we have on board, they know exactly in which direction they're looking, so they know exactly where they are pointing. And then when we move the spacecraft around, the star background changes, and the star trackers map again the new stars and decides, okay, I was looking in this direction, and now I'm looking in this direction. And this works fantastically well, especially on Mars Express, because basically without star trackers you would be dead.
Yes,
but
that's a different story.
That's a different story. Come upstairs and ask us. The problem is that on board TGO, the star trackers, when we are lost in space and they don't know where to start from, well, they basically do not even see the stars. They don't acquire. We are not too sure why they're doing that. It's most likely a software issue, but we don't have access to it, so we have to live with it. So how do we deal with that? Well, the answer is quite short, but it took us quite some time to solve this problem. We have on board what are called gyroscopes. So they are like, what is this called in English? A top spinner?
A spin top, yes.
A spin top, yeah. So these things that you start rolling and they just turn and they stay. And we have several on board, and when we move the spacecraft around, it changes the speed at which they turn, and the onboard computer can calculate the movement, and therefore can guess in which direction it's moving. The problem with those is that they are actually quite fragile. They use lasers, and they start breaking after some point. So we don't like using them so much for calculation. We don't like to depend on them. So when we do a slew with the spacecraft, when we point to another direction, we have created a little program where we basically tell the spacecraft, this is what you should be seeing. And then the spacecraft starts thinking, oh, is it really? So it's going to check if there is a star at the end of each triangle, and then it's going to go, oh yeah, you're right. And then it's going to find the other stars, and it's going to start tracking, and everything's going to be fine. So it's kind of reverse logic, you know, like when you have a child and it doesn't want to go to bed, and you tell you, oh yeah, well, fine, don't go to bed. And the child goes, oh, you know, actually I'm tired, I'm going to bed. That's what we do. I've got two sons. Okay, the last one is actually something really nice. It's actually something for you guys. This is a brand new thing that happened with TGO Wednesday evening. We were contacted by the SETI Institute. I guess you are familiar with them. They are listening for extraterrestrial activity, and they try to understand what would a message from space be like. And they decided to actually do a simulation with that. So they contacted us, they gave us a message, coded, which we loaded on board TGO, and then on Wednesday evening we radiated this signal to the Earth, talking green. And there were 3 big telescopes around the Earth that were listening to this message. One was Medicina in Italy, one was in South Africa, and the last one was in the States. I cannot remember which ones they were. Anyway, these 3 telescopes got the message, recorded it, put it together, and then if you go to the website which is indicated here, you will find the message that was sent from TGO, that was sent from space. And now the game is, what is this message? Is it a picture? Is it a sound? Is it star coordinates? Is it a joke? Some of my colleagues tried to crack it and they didn't manage. So, be my guest. There are several ways to communicate with the communities trying to crack the message. We were told that it's not designed to be cracked by one single person, it needs to be done by a team. So, yeah, give it a try. Any questions? Then have a nice afternoon. We have another panel later today. We will room and yeah, just ask all the crazy questions that you are thinking about, because that's the fun part.
Vielen Dank, dass ihr euch das Video angesehen habt. Wenn es euch gefallen hat, dann lasst einen Daumen nach oben da. Hier habt ihr nun verschiedene Auswahlmöglichkeiten. Ihr könnt oben links unseren Kanal abonnieren. Oben rechts geht es weiter zu tollen Videos von diesem Event. Unten rechts gelangt ihr zur Internetseite vom nächsten Event. Zu guter Letzt kann ich euch noch den Space Store empfehlen. Hier gibt es alles Mögliche an Fanartikeln zu euren Lieblingsserien und Filmen. Bis demnächst auf diesem Kanal.